We will study the input-output characteristic of N-channel MOSFET. So open Proteus, go to new project, name it, suppose I am writing it input, output. Create a schematic. Do not create PCB, no firmware. Firmware, we select create firmware when we use microcontroller. Since no microcontroller is being used, so no firmware project. Then finish. So this blank will appear. Go to P, select the component here P. At P click, you will get the option MOSFET. Now from here you can select a MOSFET. Suppose I am selecting this MOSFET 2N7002. This MOSFET 2N7002. Select a MOSFET, place it here, and then go to the generator. Apply a DC source at drain, and a DC to gate, and a ground. Select from here terminals, ground, place it here, connect the source to ground this way. So just I am enlarging it so that you can see it properly. Here you can name it as VDC. Right click, edit properties. You can name it as VGetToSource. Now place OK. Now you want to see the input characteristic. For input characteristic, we plot input drain current versus gate to source voltage. So go to this graph. Yes, here transfer. Take transfer because transfer input and output. The curve between input and output is, for that you take graph as transfer. So just select the transfer graph, place it here, and now you want to plot ID versus gate to source. Our target is to plot ID versus gate to source. So for that, take a probe, current probe. You have to measure ID. So select a probe, rotate it clockwise in this direction, and now just drag it and put it to the graph here. This right click and go to the edit properties. Our source one is gate to source voltage. For input characteristic, we want to plot gate to source voltage versus ID. So suppose we have the start value 0 to, suppose take it at 3 volt. So it will sweep gate to source voltage from 0 to 3 volt. Let's plot for multiple drain to source voltage. Suppose one Y has kept VDC drain to source voltage 1, suppose other has taken it 2. So for multiple VDC, we are plotting the curve, that is ID versus VGS for multiple VDC. So let's do it for 1 volt, check it what 1 volt. No problem, no issue. Then go and simulate graph. As you simulate graph, it takes some time. Now you can see the plot. These are the plot. Just right click and you can see maximizing. So you can see these are the plot. X axis VGS, get to source voltage, versus ID. Current is ID. For different VDS. For this, or you can for just right click here. So you can see here. So this gate to source, you can see here, is 2.94. This here you can see it is 2. I just click it here. Get to source 2.94. ID is 28.2 milliampere, 28.2 for VDC 1 volt. This was our topmost curve, VDC. Here we have shaped the VDC from 0 to 1. So these are for different VDC. This plot, this plot, this plot. You can see for higher VDC, you are getting a higher current. Here for same VGC, for same get to source voltage, for higher VDC, we are getting a higher current. For example, for this VDC, here the current we get to source 2.93, VDC is 500 millivolt, and the current is 21.2 millivolt for this. And for this, here for this curve, same get to source voltage is 2.92, same line here, and drain to source voltage is 1 volt, and you are getting a larger current compared to this curve. So these are for different VDC, the VDC 1, VDC 2, VDC 3. Suppose one wire has kept VDC this voltage and then he is changing get to source voltage. Other has kept VDC this and then changing get to source voltage. So these are for multiple VDC. One other thing, for example, you want to plot the curve for only one VDC. Just right click it, edit property. Suppose you want to plot only for 1 volt. Just put it 1 and go here and edit properties. Only get to source is changing, then to source you are not sweeping it, just put it none. Only get to source are changing, VDC 1 volt I have kept. Only one graph will be there. Only one graph will be there for VDC 1 volt. You can see this also. Just go and simulate graph. Simulate graph. So here is the plot. You can see only one plot. This is for VDC, only 1 volt. We are not changing VDC. You can see here. We are not changing VDC. Second source none. Only get to source we are stripping. On x-axis you can see. And VDC we have kept only not changing. We are not sweeping it. We have fixed it for 1 volt. So only one plot is coming. That is only for VDC 1, and the boy who is performing the experiment is changing get to source voltage. So input characteristic ID versus V get to source. You can enlarge it. Maximize, and you can see. Suppose just click it here. Just click. You can see here on x-axis. Here you can see get to source 2.89 and current QID. You can change it as ID. I have not changed, so it is showing QID. The drain current 25.6 milliampere. This is the current. You can see here that this is the almost this 2 to 2.4 is the threshold voltage. You can see here. This is here somewhere the current is significant. So somewhere here is the threshold voltage. Other thing is that if you want to calculate the transconductance, that is GM. GM is delta ID versus delta get to source. Change in ID with change in get to source for a given VDS. For a given VDS, suppose here VDS is drain to source voltage is 1 volt. For 1 volt we are performing the experiment. We are changing get to source voltage. So what is the rate of change of ID for get to source? You can take two value to close value, and then you can take get to difference of get to source voltage, and you can easily calculate. I will request you to calculate the transconductance, GM, transconductance of this MOSFET. From this plot we can observe the threshold voltage, it is somewhere here. And second thing, to obtain the transconductance that will be required in your small signal analysis, you can easily calculate that change in ID versus change in VGS, for which this curve is for keeping V drain to source voltage is constant at 1 volt. So you can calculate. Now we move to the output characteristic. I am deleting this graph. We will move to output characteristic. So again, go to this graph, take the transfer and plot, drag the ID here, just place this ID, drag here and right click, edit properties. Source 1 is drain to source voltage, VDC, drain to source. Okay, VDC I have written, it is VDS, drain to source. You can rename it if you want to rename it. You can rename it also. Edit properties. There is nothing name. No issue in the name. You can write it VDS also. No problem in that. Okay. So VDS, this time I will change it. VDS I will not take in constant. I will sweep it. So this is VDS. This is V get to source voltage. I will plot ID with VDS. ID for ID versus VDS. ID versus VDS for different V get to source. Suppose one wire has kept VGS 2 volt and then he is performing the experiment, that is he plotting ID versus VDS. Again second wire came, he kept VGS as 3 volt and now he started performing the experiment, that is measuring ID versus VDS and ID, plotting ID and VDS. So in this way, how will be the plot? So just drag it, I have already dragged it, go to edit properties. This is drain to source. Suppose we are changing it to 1 volt. Now suppose on for different gate to source, again keep it, we are changing it to 3 volt. Okay, right click it and simulate graph. So you can see this curve. This just I am enlarging it, maximizing it. You can see this x-axis is gate to source voltage. Suppose this is the plot of ID versus V gate to source. This is for one VDS, this is for second VDS, this is for third VDS. Just place the cursor here. You can see here at this point. Here at this point, drain to source voltage is 708 millivolt, and your gate to source, here you can see the gate to source voltage, the gate to source voltage is 3 volt and the current is 28.6 here for this. Now here for this you can see second this curve gate to source voltage is around 2.7 volt. It's around 2.7 volt and your ID is 16.6. You can see this. You can see this. So this way, in this way, you can obtain the plot of input output of MOSFET. You can also see that for the small change in gate to source, there is a large change in ID current. So this region is suitable for where the current is almost constant with respect to VDS. This region is suitable for amplification. So you can see for different gate to source voltage, VGS1, VGS2, VGS3, and keep changing VDS, drain to source voltage. This is drain to source voltage. These are the plot. Suppose this one wire has kept VGS this value that is kept VGS as 3 volt, and now he has started changing VDS and plotted and measured the current. This will be the plot. So this is the curve between ID and V drain to source. Here you can see V drain to source for different VGS. This is for VGS1, VGS2, VGS3. You can see this. So okay, let me plot it for a larger value. Suppose edit properties, we are going to get to source 3 now. Drain to source. Drain to source, I am making it as 4. Okay, you can see simulate graph. So this is the plot. This is the plot. Maximize it. You can see the current is all constant. The current is almost constant. This region is called saturation region, suitable for amplification. Only depend on gate to source voltage. Therefore, this gate to source voltage is 2.4 volt, and the current is 6.7 milliampere. For this curve, gate to source voltage is 2.7 and the current is 17. The current is changing. The current is changing only due to gate to source voltage. It is independent of drain to source voltage. You can see, and there is a large change in drain current with a small change in gate to source voltage. So it is suitable for amplification, and it is independent of other drain to source voltage. It depends only on input. And for there is a small change, there is a large change in output. So it is suitable for this region called saturation region. Is suitable for amplification. Here this region is called ohmic or linear region, and the current, as you goes on decreasing the gate to source voltage. It depends upon gate to source voltage. If gate to source voltage is very small, there will be no channel, and if there is no channel, the current will be negligibly small. That is called cutoff. So you can see increasing gate to source voltage increases current, decreasing gate to source voltage decreases current. So we studied the input output characteristic of N channel enhancement type MOSFET.